Download this code from codegive.com, link in the description below. Buffer overrun warning while writing to dynamic array, a deep dive. A buffer overrun, or buffer overflow, is a critical security vulnerability that occurs when a program attempts to write data beyond the allocated boundaries of a buffer, a region of memory used to store data. This can lead to unpredictable behavior, system crashes, data corruption, and even allow malicious actors to inject and execute arbitrary code. When working with dynamic arrays in languages like C and C++, which offer direct memory management, you need to be particularly cautious to avoid this issue. This tutorial will cover the following. 1. Understanding buffers and memory allocation *A recap of how memory is allocated and used by your program. 2. What is a buffer overrun? Detailed explanation of how it happens and its consequences. 3. Dynamic arrays and memory management * focus on allocating, resizing, and deallocating memory for dynamic arrays. 4. Common causes of buffer overrun in dynamic arrays * explores typical code patterns that lead to this vulnerability. 5. Code examples with and without vulnerabilities * illustrates the problem and safe solutions. 6. Prevention techniques * strategies and best practices to avoid buffer overruns. 7. Detection tools and techniques * methods to identify buffer overruns during development and testing. 8. Language-specific considerations, C/C++. Some nuances specific to C/C++ are covered. 9. Mitigation techniques * security measures to reduce the impact of buffer overruns if they occur. 1. Understanding buffers and memory allocation. In computer programming, a buffer is a contiguous block of memory allocated to store data. Think of it as a container with a fixed size. Different types of memory allocation exist. Static allocation * memory is allocated at compile time, and its size is fixed. Example, int myArray 10, the array myArray will always hold space for 10 integers. Stack allocation * memory is allocated on the program's call stack, usually for local variables within functions. Memory is automatically deallocated when the function returns. Example, int myFunction, int localvar equals 5, localvar is allocated on the stack. Dynamic allocation * memory is allocated at runtime, while the program is running, using functions like malloc, C, or new, C++. The programmer is responsible for managing this memory, allocating and deallocating. Example, int * dynamic array equals, int * malloc, 10 * size of, int. Dynamic allocation is crucial when you need to create arrays or data structures whose size is not known until the program is running. However, it also brings the responsibility of manual memory management, and that's where buffer overruns often occur. 2. What is a buffer overrun? A buffer overrun, also known as a buffer overflow, happens when you write data past the end of the allocated memory buffer. Imagine you have a box that's designed to hold 10 items. If you try to force 12 items into the box, the extra 2 items will spill over, potentially damaging the other items around it. Here's how it breaks down. The cause writing more data than the buffer can hold. This usually occurs because of incorrect calculations of the required buffer size. Missing or incorrect bounds checking. Using functions that don't perform bounds checking, example strcpy in C. The consequences data corruption overwriting adjacent memory locations can corrupt data used by other parts of the program, leading to unexpected behavior or crashes. System crashes overwriting critical system data, like return addresses on the stack, can cause the program or even the entire operating system to crash. Security vulnerabilities. The most severe consequence is the ability for attackers to inject and execute malicious code. By carefully crafting the data written past the buffer, an attacker can overwrite the return address of a function, causing the program to jump to the attacker's code instead. 3. Dynamic arrays and memory management. Dynamic arrays provide the flexibility of resizable arrays. They are implemented using dynamic memory allocation. Here's a breakdown of the essential operations. Allocation. Using functions like malloc in C or new in C++, you allocate a block of memory large enough to hold the initial number of elements. Resizing. When the array becomes full, or you need to reduce its size, you reallocate the memory block using functions like realloc in C or new and delete in C++. This typically involves 1. Allocating a new block of memory with the desired size. 2. Copying the contents of the old block to the new block. 3. Deallocating the old block. Deallocation. When you're finished with the dynamic array, you must deallocate the memory using free in C or delete for arrays, in C++. Failing to deallocate memory results in a memory leak, which can degrade performance and eventually lead to system instability. 4. Common causes of buffer overrun in dynamic arrays. Incorrect size calculation. When allocating or resizing the array, you might miscalculate the required memory size. For example, forgetting to multiply the number of elements by the size of each element. Missing bounds checking. Failing to check if the index you're writing to is within the valid bounds of the array. This is a classic error when iterating through the array. Using unsafe functions. In C/C++, some standard library functions are inherently unsafe because they don't perform bounds checking. A prime example is strcpy, which copies a string from one location to another without limiting the number of characters copied. Off by 1 errors. Writing to array size when size is the number of elements in the array, valid indices are 0 to size 1. Integer overflow. In some cases, an attacker might be able to cause an integer overflow in the size calculation, leading to the allocation of a smaller than expected buffer. 5. Code examples, C/C++. Example 1, vulnerable code, C. Explanation. 1. We allocate a buffer of size 10. 2. Strcpy attempts to copy a much longer string into the buffer. 3. This overwrites memory beyond the allocated space, leading to a buffer overrun. 4. The effects may be immediate or deferred. The program might crash immediately, output junk data, or the crash might occur much later. Example 2, safe code, C, using strncpy. Explanation. 1. We use strncpy instead of strcpy. 2. strncpy takes a third argument, which specifies the maximum number of characters to copy. We set this to size, 1 to leave space for the null terminator, \0. 3. We explicitly add a null terminator at the end of the buffer to ensure it's a valid C string. 4. Now, even if the source string is longer than the buffer, strncpy will only copy a limited number of characters, preventing the overrun. Example 3, vulnerable code, C++. Explanation. 1. We allocate an array of 5 integers, indices 0 to 4. 2. The loop iterates from I equals 0 to I equals size, which is 5. 3. When I is 5, my array 5 accesses memory outside the allocated array, causing a buffer overrun. Example 4, safe code, C++. Explanation **. 1. Instead of raw pointers and new/delete, we use std vector, a dynamic array class from the C++ standard template library, STL. 2. Std vector handles memory management automatically, resizing the array as needed and deallocating memory when it goes out of scope. 3. We corrected the loop condition to iterate from I equals 0 to I size, ensuring we stay within the valid bounds of the array. 6. Prevention techniques. *bounds checking *, always verify that the index you're using to access an array is within the valid range, 0 to size, 1. Use assertions during development to catch out-of-bounds accesses early. *size calculation accuracy * double check your calculations when allocating or resizing memory. Ensure you're multiplying the number of elements by the size of each element. Safe string handling avoid strcpy and sprintf in C/C++. Use strncpy, tinprintf, or even better, use C++ std string. These safer alternatives allow you to specify the maximum number of characters to copy, preventing overruns. Use higher level abstractions use data structures like std vector in C++ or equivalent dynamic array structures in other languages. These classes handle memory management and bounds checking, reducing the risk of errors. Defensive programming assume that input data may be malicious or invalid. Validate all input values before using them to allocate memory or perform calculations. Code reviews have your code reviewed by another developer. A fresh pair of eyes can often catch errors that you might miss. Static analysis tools use static analysis tools to automatically detect potential buffer overruns in your code. 7. Detection tools and techniques. Compilers with buffer overflow detection modern compilers, like GCC and Clang, often have built-in features to detect buffer overflows at compile time or runtime. Enable compiler flags like fstack protector, GCC, or fsanitize equals address, Clang, for runtime checks. Memory debuggers tools like valgrind, Linux, and address sanitizer, ASAN, can detect memory errors, including buffer overflows, at runtime. They insert instrumentation code into your program that tracks memory usage and reports errors when they occur. Fuzzing fuzzing is a technique where you automatically generate a large number of random or semi-random inputs to a program to try to trigger vulnerabilities, including buffer overflows. Tools like AFL, American Fuzzy Lop, are commonly used for fuzzing. Dynamic analysis run your program with various inputs and monitor its behavior for signs of memory corruption, crashes, unexpected behavior. Static code analysis tools utilize static analysis tools, example Coverighty, Fortify, to scan source code for potential vulnerabilities without executing the program. They use pattern matching and data flow analysis to identify buffer overruns. Debuggers use debuggers, example GDB, Visual Studio Debugger, to step through the code and inspect memory locations to detect memory corruption. 8. Language-specific considerations, C/C++. C provides very little built-in protection against buffer overflows. It's up to the programmer to be extremely careful with memory management and bounds checking. The standard library functions like strcpy and sprintf are notorious for their lack of safety. C++ offers some advantages over C due to features like classes, RAII, resource acquisition is initialization, and the STL. Using std string and std vector significantly reduces the risk of buffer overflows compared to using raw character arrays and malloc/free. However, you still need to be careful when working with raw pointers and manual memory management. 9. Mitigation techniques. If, despite your best efforts, a buffer overrun occurs in a deployed system, some mitigation techniques can help reduce the impact. Address space layout randomization, ASLR randomizes the memory addresses of key program components, libraries, stack, heap. This makes it harder for attackers to predict where to inject their code. Data execution prevention, DEP, /no execute, NXDEP marks certain memory regions as non-executable, preventing attackers from executing code that they've injected into those regions. Stack canaries. A canary value is placed on the stack before the return address. If a buffer overflow overwrites the canary, the program can detect the corruption and terminate, preventing the attacker from hijacking control. Safe libraries and frameworks. Utilize frameworks and libraries with built-in protections against common vulnerabilities. For example, using safe string handling functions. In summary, avoiding buffer overruns is crucial for writing secure and reliable code. By understanding the underlying principles of memory management, following best practices for bounds checking and safe string handling, and utilizing appropriate tools for detection and mitigation, you can significantly reduce the risk of this common and dangerous vulnerability.